Hello, good afternoon, everyone, and thanks for joining us for this second webinar on educational neuroscience that we are, as a Faculty of Education, launching together with University College London and the Educational Neuroscience Hub in order to promote educational neuroscience towards educators and to promote practices in schools. This is our second webinar, and today we have the pleasure of having Professor Andrew Tolmie, who will be discussing another area of neuroscience, and Michelle later on will introduce him and the team. I will just take you through some the structure. Erica will then tell us something about education neuroscience and why it is important. Michelle will introduce today's speaker. We'll have the presentation, and following that, we'll take some questions and we'll do some discussion on the issues that you raise based on the presentation. We would like you to include any comments, feedback, or questions in the chat if you would like to, and then we can refer to those questions and comments in our follow-up discussion following the presentation. Following these two webinars, we plan to have a series of webinars between October and December next scholastic year. So these are just a taster of an idea of education neuroscience that we hope will create and generate discussion amongst educators. I think I'll leave it up to you, Erica, so that you can just give your thoughts about why education neuroscience is so important. Thank you.
Thank you, James. First, I would like to thank Professor Andy Tolmie for accepting our invitation to give an overview of this insightful area within maths and science. As mentioned last week, the Education Neuroscience Hub is collaborating with the Faculty of Education within the University of Malta and the Center of Education Neuroscience at UCL and Birkbeck in order to create more awareness locally amongst faculty members, teachers, educators, policymakers, parents, and other professionals within the educational field on this innovative and pioneering topic. It aims to create a better understanding of the development of the brain within the context of teaching and learning. And more importantly, it also aims to create that bridge, that common language between science researchers and practitioners, and also parents, enhancing evidence-based strategies within the context of teaching and learning. Over the past few decades, we have experienced a revolution in brain studies, gaining a better understanding of complex human behavior. And with this knowledge, we can empower teachers and parents to reach out to their children in a more holistic manner, emotionally, socially, cognitively, and behaviorally. The Education and Neuroscience Hub will be organizing seminars, talks, webinars, and workshops independently and in collaboration with the Faculty of Education at the University of Malta and the Center of Education and Neuroscience, in order to promote ways in which education neuroscience can inform classroom instruction amongst the local educators, schools, as well as parents. If you would like to be updated and notified about these initiatives, I'll be placing the Education Neuroscience Hub Facebook page link within the chat. Thank you. I hope you enjoyed the talk, and on to you, Michelle.
Yes, thank you, Erica, and welcome, Professor Tolmie. Thank you for accepting to contribute to this webinar. So in his talk, Professor Tolmie will refer to how children's ability to understand counterintuitive concepts in science and in maths is often limited by their ability to inhibit either direct perceptual evidence or pre-existing beliefs, impeding their learning. And using evidence from educational neuroscience, this session will examine why this is so and explore how to address these challenges, drawing out more general messages about the ways in which neuroscience can inform classroom interventions. So that's all from my part, a brief introduction on the talk, and I now invite Professor Tolmie to start his speech, his lecture.
Many thanks, Michelle. Many thanks to James and Erica as well for setting this up and for the invitation. Let me just share my screen to get the slides that I'm going to use up there. So is that visible? Can everyone see those? Okay, great, thank you. Let me just put that into slideshow. So yes, this is very much intended to be a follow-on from the talk that Michael Thomas, director of the Centre for Educational Neuroscience in London, gave last week. And basically what he was trying to do was to kind of provide you with some kind of idea of what educational neuroscience is and what its objectives are. So for those of you who were able to be there for that talk, you'll have picked up on some of that. What I want to do today is really just kind of go on to examine what this might actually mean in practice. So thinking about the actual practicalities of what using educational neuroscience might actually look like. So this is one example based on a project, the Unlock project, that you can see the logo for down in the bottom left of the screen, that we've been running over the past few years. But we'll try to draw out some more kind of general messages as we go through, and perhaps we can talk about those in terms of other strategies in the discussion after the presentation. So as Michael was saying, really, the goal of educational neuroscience is to provide neuroscience and other types of evidence that are available to us from scientific research to provide a deeper understanding of the mechanisms and the processes involved in learning. And the idea is that if we understand those the processes, the complex processes, it has to be said, involved in learning in a better fashion, and how those work out in different learning contexts, then that should provide us with better insights into how to provide teaching and organisation of classroom activities in order to promote more effective learning. So that's the kind of basic idea of educational neuroscience, about generating that kind of evidence base to provide us with some sense of what strategies we might use to improve learning more generally. There are a multitude of questions that spin off that, and I'm not going to get into those today, though we might pick up on some of that in the discussion later. But I think the kind of key thing, thinking about this in practical terms, is that the outcomes of this kind of work are essentially behavioural approaches to providing instruction, supporting learning, which are based on evidence from neuroscience, from psychology, developmental psychology in particular, about how the brain works and how cognitive strategies, cognitive processes involved in learning are embedded within neural processes, and how that therefore tells us what kinds of activities we should be engaging in order to promote learning. So the impact is necessarily an indirect one. It's not about actually kind of providing using neuroscience and related approaches directly to provide learning. It's about thinking about the behavioural strategies that are implied by that kind of evidence base. So that's really what I want to kind of identify as a kind of exemplar through the presentation today. And when we're doing this kind of work, regardless of specific context, I think there is a general sequence of activity that we're engaged in. So the start point is always thinking about some specific problem, and then that we want a solution to, and particularly ones which are of educational importance. So identifying the problem, analysing that problem and its potential sources, what the kind of issues might be that lead to the problem in the first place, and in particular how that might be something which is affected by neurocognitive processes of one kind or another, and therefore on the basis of that to try to identify a strategy for addressing it, and then develop that strategy and design, test, evaluate, and implementation based on that. So that's the kind of general sequence. There are, various complexities at each stage of that, and we'll perhaps touch on some of that as we go through. But basically, that's the kind of sequence of events that I want to try to kind of take us through in this particular session this afternoon. So the focus for this, as Michelle has said, is on misconceptions, particularly in science and maths. As I said before, we need to start by thinking about, well, what's the problem here? and then trying to kind of analyze it a bit further. And the key thing, I suppose, is that in both science and maths, there's evidence from over 30 years, in some contexts going back a lot longer than that, on the misconceptions or poor conceptions, might be a better term sometimes, that children hold regarding, so for instance, scientific phenomena. So there's an example here, which you may be familiar with, which is a tendency, I mean, indeed, this is not just children, many adults have this kind of belief too, that things when they're in a circular motion will remain so once they become unconstrained. So if you think about this in terms of the kind of example shown on the screen here, if you show people the context of a ball rolling down a spiral tube and then ask them what trajectory it will follow once it's exited from the tube, then many people, perhaps as many as 30 to 40% of adults still, will say that, that it will continue in a circular path once it's exited the tube. And the percentage of children who think that's the case is very much higher. Whereas people shown in the context of a ball rolling down a straight tube would be very rarely would say that the ball would exit with a circular trajectory, that understand that it would have a straight on trajectory, which of course in fact is what it would have in both instances once the constraint on the movement has actually been released. So the idea here is that people think that things that continue in the kind of motion, even with constraints that has already been going on, and they will continue to do so once they've been released from that. So this is one kind of example of a typical misconception in the context of forces within physics. There are many other areas of science and maths where you see similar problems, and to take some other instances of those, first of all from the context of maths, and Michael in his talk mentioned some of these examples last week. So children spend the early part of learning about the nature of numbers and how numbers, as the units increase, the numbers get bigger, and then they encounter fractions where the exact obverse applies. So there's a very common tendency to think that 1/3 plus 1/4, you simply add those things up. So in order to arrive at the answer, so 1/3 plus 1/4 equals 2/7, which is plainly incorrect. So they're failing to appreciate something about the nature of the relationships implied by the kind of fractions. And similarly, we think about this in terms of relative size. They're used to thinking, children are used to thinking that 10 is bigger than 9, but when they're presented with 1/10, and 9/100, they'll tend to think that 9/100 is bigger because it's got a bigger number in it, i.e. 100 rather than 10. So they need to learn something about the nature of the relationships implied by these kinds of expressions, and to put, in some senses, their ideas about numbers, whole numbers as they've encountered them up to that point, on hold whilst they do that. And similar things in science. So learning that, for instance, a dolphin is not a fish, even though it swims in the sea like most fish do, or all fish do. But it's actually a mammal that has adapted to life within within a marine context. So there's kinds of conceptual categorization errors that are made in that. And other examples from forces, there's a great tendency for people to think that the heavier objects fall faster and through air under gravity than lighter objects. So if there's no air resistance, which falls faster, a hammer or a feather, most people would still tend to say a hammer rather than a feather, but in actual fact, if there is no air resistance, then the rate of descent under gravity is exactly the same for both objects. So weight makes no difference whatsoever. So there's plenty of examples of these misconceptions, and a number of textbooks which have tried over time to catalogue these misconceptions and why they might arise. And there's been a lot of work on the various sources to different misconceptions, and I think it's still fair to say that we don't understand very clearly exactly what the processes that lead to these kind of resistant ideas might be. And certainly it seems unlikely from what we do know that there is any one single reason that's at work here. It depends a lot on the material that we're actually dealing with and how people have encountered it, how children have encountered it to begin with. So there's a variety of factors at work, including the plausibility of intuitive ideas. Michael was using an example last week of the Earth plainly being flat, despite the fact that that it isn't. So plausibility of intuitive ideas. Often there are things to do with inaccurate notions passed on by adults. Certainly in my own work, we've documented the way in which children are very highly influenced by, in terms of scientific concepts, by the things that they hear from adults. So those ideas are held as misconceptions by adults, then those will tend to be passed on to children, and they will kind of have something of the same kind of idea as well. So certainly things to do with weight might be coming from that kind of context. Early ideas which are unsophisticated but need and then over applied. So that would certainly be the case in the context of thinking about number relationships versus fractions. So there's lots of different sources, lots of different reasons why these misconceptions might arise. And what we want to do, obviously, in an educational sense, is to find clear strategies for addressing these and making sure that the path towards getting better conceptions is actually made easier for learners. And of course, further implication of this is that counterintuitive ideas are likely to be particularly prone to misconception. So we've been very much focused on what happens when children encounter counterintuitive ideas and how do they actually come to be able to deal with those in appropriate fashion. So there is a lot of literature, as I say. There's been work on misconceptions that's been going on for 30 plus years. And in terms of educational strategies to address these, much past work has tended to assume that the best approach to these misconceptions is to, in some sense, tackle them head on in order to promote some form of conceptual change. And the notion here really has a very strong origin in Piagetian ideas of cognitive conflict and re-equilibration. So Piaget's notion was that much learning takes place throughout the child's development. Much of their understanding of the physical world, for instance, comes about through the conflict that they experience between their existing ideas and their experience as they actually encounter novel instances of the world. And basically that conflict between what they experience directly and what they originally thought sets up a kind of uncomfortable sensation of mental perturbation, if you like. And they need to engage in some form of process of conceptual cognitive re-equilibration in order to balance out the new information with the existing ideas. And that, in Piaget argued, will tend to lead to more inclusive, more refined concepts over time. So that basically there's a process of conceptual change and conceptual improvement that comes about through experiencing these conflicts. And subsequently, it's an idea that Piaget espoused himself, though he never did any work on it, the idea that actually you can set up this kind of conflict not necessarily by relying on children encountering things which are different to what they originally expect, but if you put them into a situation of discussing their ideas with other people, peers particularly, and they find that their ideas are different from those of other people, that sets up the similar kind of conceptual conflict. So much of the work on how to reduce misconceptions is focused on this idea of conceptual conflict in situations of collaborative learning. Much of my own work over a period of time was based on exactly this. So what that work does is to use predict, test, explain tasks, especially during the primary school years, in order to actually set up these circumstances of conceptual conflict between peers working together on a problem. So basically what would happen in this kind of task, say for instance, it's to do with which objects float or sink in a tank of water, then we would first of all ask the children working in, say, a group of 4 to make individual predictions about what they think will happen to each of a set of objects when it's placed in the water. And then they proceed to discuss their individual predictions, test them out, and then explain what they've actually witnessed. So there's a kind of series of potential steps involving conflict involved in that. So in the predict stage, when they're comparing their predictions, they may find that other people have got different ideas about which objects will float or sink, and so they need to address those. Then when they test them out, the idea is that they have to agree a prediction between them, and they test those out. And if they find that the result of the test is different from what they collectively decided to back as a prediction, then they have to explain why that's the case as well. So there's various stages of conflict involved in this, and potential for that kind of idea of re-equilibration. Much of the work that's been done on that has found that this approach is actually successful, and it seems to, in particular, to lead to change over a kind of a longer period of time, which suggests that it is actually this process of underlying re-equilibration that certainly is part of what's involved in that kind of that conceptual change. More recently, though, and this is really where the educational neuroscience comes in, more recently, though, neuroscience work has shown that the conflict and change of that kind are not the only mechanisms that seem to be at work when we're dealing with these kinds of changes in conception. And it's that I want to kind of have a look at next. So in particular, what has been suggested through some of this work is that that learning in maths and science, and particularly perhaps in the context of counterintuitive beliefs, learning in maths and science sometimes involves inhibiting prior beliefs, and where those have been derived, where those have been derived from direct perceptual information, in inhibiting that information as well, in order to actually grasp some more difficult and less obvious idea that might lie behind it. And so in terms of the kinds of neurocognitive systems that are involved in that, we understand something from how those work, from a great deal of work on executive functions, as we call them. So different aspects of neurocognitive control of cognitive processes. And in particular, we understand from that that inhibitory control, one of the central processes of executive function, relies on the activity within the anterior cingulate cortex, the dorsolateral prefrontal cortex, and the ventrolateral prefrontal cortex. And basically what these systems do, as we understand it, is that the anterior cingulate cortex detects conflict between an experience and some prior belief, or some kind of instruction, perhaps, and prior belief. So it detects that there is some kind of conflict there, and it activates the dorsolateral and ventrolateral prefrontal cortex to manage that kind of that conflict. And how that often happens is simply by suppressing the activations from existing systems in order to actually take in new information. So this is neatly kind of laid out in a paper by my colleague Denis Marichal from 2016 in the Current Opinion in Behavioral Sciences. But there's much work that we find elsewhere talking about these inhibitory control processes. So why is that relevant? Well, what we some more recent evidence suggests is that that rather than people who become experts in science learning through a process of conceptual change and losing those misconceptions, what that evidence suggests is that experts actually get better at inhibiting those established responses rather than replacing those prior concepts with new ones. So to take an example, there's a number of studies now that have looked at this, but to take one of the first examples, Masson et al. From 2014, what they did in this particular study was to present misconception-related stimuli, which was in the form of electrical circuits. I'll show you some examples of those in a second. So basically, they presented both impossible circuits and well-formed circuits to physics experts and novices, and asked them to think about whether the depiction of lights coming on within those circuits was accurate or not. And what Masson et al. Found was that the experts who accurately judged inappropriate circuits to be non-scientific and accurate circuits to be scientific. So their judgments are accurate. They also showed increased activation in the dorsolateral prefrontal cortex and associated regions, those that I've just been talking about, compared to novices who judged the stimuli to be the incorrect circuits to be scientific. So to kind of give you an illustration of that, we have these kinds of materials here. So we have control circuits in which lights come on. There are complete circuits in both instances. In scientific circuits where there's an actual circuit with a light coming on, and a branch off flat where the light doesn't come on because there's no completed circuit involved in that. And then an example of similar fashion where we have lights coming on both in the circuit itself and in the branch off, which is actually not what would happen. And we have these kind of mappings of activations in the brain from the experts versus novices as part of that. Without going into a huge amount of depth about this, you should be able to see that when experts were presented with the non-scientific circuits, we see increased activations relative to the novices in exactly those areas I was just talking about within the dorsolateral prefrontal cortex and the anterior cingulate, suggesting that there is actually some active process of suppression, inhibition going on to stop the experts endorsing the non-scientific evidence. So they've learned to suppress that and to replace to guide their response by something that is generated separately from that. So what this suggests, if we take this seriously, is that these misconceptions or automatic naive responses don't go away for the most part, but they're actually we actually have to learn to suppress them in order to then learn and to retrieve correct and often counterintuitive answers. And actually that notion is not inconsistent with some of the things I was saying just now about collaborative work in learning science, because it might be that exposure to those conflicting viewpoints within the collaborative context might also actually be serving to activate inhibitory control. You learn to be more careful about what you say because you realize that actually other people do have different points of view, and that in itself is the beginnings of being able to inhibit spontaneous ideas. And we'll pick that theme up a little bit later when I talk about the Unlock project. And to check this out a little bit further within the specific context of science and maths problems, Annie Brookman-Byrne, one of my former PhD students, examined the role of inhibition by testing 11 to 15-year-olds on a range of both science and maths misconception items, and on both motor and semantic inhibitory control. I'll say more about that in a moment. So the kinds of tasks that we're using for the science and maths counterintuitive problems were of this kind here. Obviously, these are just specific instances. So you can see for the science problem set, this is about the rate of fall of heavier objects and lighter objects. And basically, the participants are asked to say whether they think heavy objects fall faster than lighter objects or fall at the same speed. And they see basically either a version which invites being endorsed, so it's the false version. You see the top left there, heavy objects fall faster than lighter objects of the same size. Correct, though that's the false response, it fits in with the kind of typical misconception to say that that is correct. And then another form of wording of that, so heavy objects fall at the same speed as lighter objects of the same size, where that should be endorsed as correct, but will frequently, due to misconceptions, be endorsed as incorrect. And then control items about when an object is released without any support, what happens to it. And basically for each of these kind of problem sets, participants would see one misconception aspect of the kind of thematic of the material and one control item, so they'd either see a false or a true misconception item, a false or a true control item. So there were different problem sets generated in that way, basically so that we could be sure that the ways the problems were formulated wasn't actually affecting responses. and then we could look at a collective pattern for misconception versus control items. And we have similar kinds of problems for the maths problem set to do with, in this particular instance, the perimeter of figures, but the same kind of setup about false versus true misconceptions and false versus true controls. As I've kind of noted at the bottom of the slide here, the science problems included a range of different aspects of science: biology, chemistry, and physics. And the maths problems included things from algebra, shapes, statistics, probability, and graphs. Remember, these are secondary school pupils who are involved in this. So that was those were the items that we used to measure understanding in science and maths of counterintuitive ideas. And then we measured, as I said before, both motor and semantic inhibitory control. So basically what we mean by motor inhibitory control is stopping a response that is the kind of natural thing to do and replacing it with a response which is a motor response which is not the natural thing to do. So classic task for use of that is what's called the go, no go task, where in the simple version, basically if a green square appears on the right-hand side of the screen, that's a go response. So you press a button on the keypad of a computer when you see that kind of stimulus. And you see those repeatedly, and then items are introduced where which don't have that form. We have a red square being shown on the left-hand side of the screen. The response that's already been built up to say to press the button key has to be suppressed, and no response actually made. So that's the no-go task. So no-go trials are embedded within a range of go trials in order to create that kind of tendency towards an automatic response, which then has to be suppressed, and we measure the error rates and the time taken in order to actually perform accurately on that kind of task. And complex go, no-go task involves something of the same kind, except now the kind of response for whether it's go or no go is not based on the item itself, but on its relationship to previous items. So it's a no go if a different colored square appears in a different position to the previous go trial, but it's a go if it appears in the same position as the previous go trial. And so you actually have to kind of think doubly before before activating suppression. In the Stroop task, there is no behavioral response as such that has to be inhibited here. This is about actually controlling semantic processing of the material. So in this particular instance from numerical Stroop, basically what participants have to do is to say the number of items that they see on the screen, not the number. So in a congruent trial, there's one item and the number 1, so that's fine. There's no conflict there. They just say 1. But in an incongruent trial, we've got 4 3s, but displayed as 3s, and they need to inhibit the tendency to say the numeral in favor of the number of items that are on screen. And similarly with the 2 4s, that's a further incongruent trial, but 3 3s would be congruent again. So basically, again, what we're looking at is the kind of errors that people make on this and how long they actually take to make responses. The idea being that they will take longer to make a response if they have to engage in some process of inhibition. So what Annie found was that performance on the misconceptions, the counterintuitive item task, was directly related to individual ability on both motor and semantic inhibitory control tasks. So it did seem to be the case that those who had better inhibitory control were also better able to engage in processing information about counterintuitive problems, suggesting that there was some kind of dependency of learning counterintuitive items, responding to counterintuitive items that depended on inhibitory control of both motor and semantic levels. Preliminary imaging evidence that Annie also set up around this confirmed that there did seem to be activations in both the same areas for the misconceptions and the inhibitory control task. So going back to the active patterns of activation that were seen in the Masson et al. Study, the idea is that there were similar kinds of activations being seen for both types of both the science and maths problems and the inhibitory control tasks, suggesting that that there were overlapping circuits involved indeed, as far as that's concerned. Again, suggesting that there is some kind of direct relationship between inhibitory control, capacity, and learning of these, or being able to perform on counterintuitive problems. Okay, so that seems to suggest that, sorry, we can see something of that kind of pattern of activations here for the different trials, showing those overlaps. So that seems to suggest that in terms of our analysis of the nature of misconceptions and how we might actually adopt strategies to deal with those, it suggests that firstly, of course, teaching children counterintuitive ideas is an essential step in both science and maths learning. They need to get to engage with these counterintuitive concepts. But in order to actually do that, what we should be doing is promoting early inhibitory control to help them suppress the misconceptions, and use that as a way to help them make the best use of teaching by learning to actually suppress intuitive ideas, the first idea that occurs to them, in favor of listening and paying greater attention to the new material they're being introduced to, in order to grasp exactly what that is actually showing. So that begins to suggest a certain kind of strategy for dealing with these counterintuitive ideas. So the second stage in the process that I was talking about to begin with, having identified the problem, we now have the ground, at least a germ of an idea of a strategy for dealing with this. So we then need to think about how we might actually kind of take that forward in terms of actual design. How do we go about promoting inhibitory control if that seems to be the thing that we actually need to do, which is what that analysis suggests? When we start kind of moving into that territory, there is a further kind of issue that we need to take on board, which also is going to have to inform the strategy that we adopt. So there has actually been quite a lot of research over the years now on training children in generic executive function inhibitory control abilities. And so, for instance, training inhibitory control, one strategy for dealing with that might be to engage children in repeated practice of things like the go, no go task and the Stroop task that I was talking about just now. So they repeatedly practice those and they get better at doing that, suggesting that their inhibitory control has got better as a result of that. And those studies have typically found that if you provide that kind of training, then you do see improvements in performance on these kinds of tasks over relatively short periods of time. What has always been problematic as far as that's concerned is actually then identifying any transfer of that improvement to classroom performance. And indeed, most research, there are very few exceptions, but most research has found that there are major problems getting any kind of transfer from these generic training to anything relating to classroom performance. And the reason for that may be that actually the notion of generic training in itself is actually based in itself on a misconception. And the idea that actually when we're talking about these executive function inhibitory control systems, that these are in some sense a kind of a form of modular system analogous to a computer routine. So you just need to make sure that within your computer that the inhibitory control system is being activated when you're processing information, and that system is a complete module. You can plug it in, separate piece of software, and it will kick in when it's been activated by appropriate context. That's not actually how the brain actually functions. So the idea of thinking about training in inhibitory control as a generic function is unlikely to be true. Modularity of that kind is not how the brain organized. Instead, it consists of specific circuits that are built up over time. And those circuits themselves need to have the inhibitory control processes actually directly built into them. And that may lead to general function. There may be general inhibitory control processes subsequently of the kind that we can measure in the adolescents within Annie's study. But that's going to take a while to emerge. And if you want to actually use this as a strategy for improving learning. That's not the way to go about it. It's too slow a process. So what we need to do is to think about how we actually can build inhibitory control into performance on the material itself that we want inhibitory control to be applied to. And more recent imaging work by my colleague Irwas-Dinontai at Birkbeck has shown that the further evidence that is actually seems to be indicated as the kind of appropriate strategy, because that work found that counterintuitive inhibition and inhibition activations were only partially overlapping. So consistent, as I say, with the idea that inhibitory control actually has to be developed in the specific areas of application. You can't do it as a kind of general thing. You need to build it into the material that you actually want learners to engage with in the first place. So a slightly long story with the kind of more complex aspect of the analysis that adds in, but it was that really led to the Unlock project. So the key principles in that particular project were taking learning of counterintuitive ideas, but in particular promoting inhibitory control in science and maths learning through encounters with intuitive ideas, and learning to actually engage, pause and reflect strategies in exactly that context, rather than appealing to immediate intuitive ideas that are often incorrect. So it's about building in the inhibitory control within the encounters with the counterintuitive items themselves. And we had large-scale funding from the UK Education Endowment Foundation Wellcome Trust to develop materials to actually do this. So we developed computer-based materials to provide that kind of training, and then conducted a large-scale trial of effectiveness and also deployment of that within real schools with children in years 3 and 5 within the English primary school system. And we targeted children from disadvantaged backgrounds in particular, because we know from past research that those children are typically likely to exhibit weaker inhibitory control. So it's more important to get them engaged with inhibitory control in this kind of learning than children from more advantaged backgrounds. And in terms of the software development, what we developed was a piece of software called Stop and Think, which is based on a series of counterintuitive science and maths programs. And that was presented, these problems were presented in a kind of game show format with the assistance of a central on-screen character, Andy. I'll show you something of what this looks like in just a second. And we also ran a pilot trial with this software, first of all, in 8 schools to test the operation of that software, comparing whole class use with individual use. And perhaps again, counterintuitively, we found that the use of the software on a whole class basis was actually more effective than individual use. Perhaps going back to that point I was making previously about collaborative learning, actually engaging in these problems collectively might actually be an important part of inhibitory control, because learning in inhibitory control because of hearing the responses of others and how those might differ from your own. Okay, so that's the kind of general setup. Let's give you a kind of flavor of what that looks like. So I decided not to risk trying to show you the software live, because of the problems that there are so many things that could go wrong. So I'm just going to show you some screenshots. So basically, as I said, we've got this kind of great game show format with Andy, the host, on the left-hand side, and 3 participants, Candice, Ollie, and Kate, in the middle. And basically what happens is that the players, but of course the children themselves participating in research, are shown a problem, and they have to think about the response to that. So what number is shown by the blocks here, and they have to think about what the answer to that is and insert that answer. But you'll see down in the bottom left of the screen, we have this stop and think. And basically this was a prompt that came up on all these trials. Stop and think, don't make the immediate intuitive response. Think about it. What's the right answer to this before engaging further? So basically they have to come up with their own answer, but they're being prompted to stop and think, reflect before they actually make their answer. And then the game show participants make their own answer. So Candy says, I've counted 7 pieces in total, so that must be the answer. Ollie says there are 4 long bars and 3 spare cubes, again implying something of that kind. And in case there's the 4 bars, each have 10 cubes, and there are 3 more units to add, implying the right answer. And the study participants have to then identify which of those they think is correct. So it's about generating their own answer and mapping that onto the answer of the game show participants, and then carrying on across a series of trials, basically generating something of the same kind of activity with different types of materials, different problem contexts. So that's basically how the software operated. And of course, to give you an example of that's maths kind of example, give the example of science type things. An example problem in that context would be they were asked to click on all the pictures of living things, and again there are some tendencies for potential misconceptions here, because children tend to judge anything that is actually capable of movement as or generating movement as being alive. So there's some tendency perhaps to think of fire in particular as alive rather than inanimate. So that's the basic kind of problem design. In the full trial, what happened was that children worked on extended versions of these problems. So they worked on the software immediately prior to science and maths lessons for 15 minutes, 3 times a week over the space of 10 weeks. So you can see there's a lot of sessions that they had exposure to here, though each session in itself was relatively brief. And for the trial itself, we used 85 schools. So it was a large-scale trial from across England. And those schools were chosen from among those with highest percentage of children on free school meals, which is one of the standard indices we use in the UK for thinking about the relative disadvantage of children within different schools. So that's was the basic shape of the trial. And then we had, as I said before, year 3 and year 5 classes involved in that. And because we were deploying the intervention at class level, we couldn't have individuals in the same class assigned to anything other than one condition. So the year 3 and year 5 classes were randomly assigned to one of 3 conditions. So the intervention using the stop and think software that I've just been talking about, a business as usual control where basically they just had the kind of maths and science learning lessons that they would have ordinarily, and a control plus condition where the children worked on similar kinds of computer-based tasks to the intervention, but with a focus on developing, promoting socio-emotional skills. And the reason for this active control plus, is that we need to be careful when we're doing trials of this kind of intervention, that the reason if we see progress, if we see change, that it isn't just simply due to the fact that something different happened and the kids were more motivated simply because something interesting was going on in a way that it wouldn't do in business as usual. So the active control, the control plus, gives us a measure of the impact of just simply doing something different within the class versus the effect of the intervention itself, which is focused on specific types of learning. And we had, across the sample, we had half the sample, half the classes were assigned to the intervention edition, with a further half split evenly between business as usual and the active controls. And we used a cluster design for this, which meant basically that each school had both intervention and control classes. And the reason for doing that is that just simply because that improves, for obvious reasons, potential for recruitment on the whole, and quite reasonably. No school is very keen to be involved simply as a control within an implementation design of this kind. They want to have at least potential benefits to some of their pupils. So by using this kind of approach, it meant that no school with control only, they had some intervention classes, so their children were, at least some of their children were standing to benefit from the intervention. And the outcomes within the projects funded by the Education Endowment Foundation, there is this standard thing that you don't do your own evaluation because, of course, you're biased in favour of trying to find positive outcomes. So we have the outcomes are evaluated by an independent organisation in order to ensure there is no kind of possibility of that kind of bias. And in our case, this was the evaluation was done by the National Foundation for Educational Research. It's a standalone organisation within the UK that focuses on educational research and outcomes from that. And what they did was to use standard tests of science and maths progress and they also used interviews on the process, perceptions of the process with teachers. So the idea here is if the intervention is going to have any benefit at all, it's got to show impact on something which is actually the kinds of measures of achievement of progress that schools would be wanting to use to assess children's gains within as a result of their teaching within the school. So you can see that that's actually an attempt in many senses to provide a kind of absolute bottom line for progress. It's got to have an impact on the real things, the real kinds of achievements that measures that schools use. We also had computer-generated measures of usage of the software in order to check the relationship between progress and actual activity. As you may imagine, with deployment across 85 schools, there was always going to be the possibility of variation in the extent to which teachers actually did make use of the software in the way that they were intended to do. And also the incidence of technical problems, which perhaps might on some occasions have prevented them from making use of the software in the way that was intended. So we needed to kind of track that level of activity to see if that actually had any impact on the effects of the intervention itself. Again, we were using that kind of idea that I was talking about before of making sure there's no kind of chance of bias in the data that's collected. The project staff were blind to who were blind to the condition that children were in, also collected data using measures of inhibitory control, which they then passed on to NFER for analysis. So we have measures of general inhibitory control capacity as well. And for a very small set of the participants who were accessible to our centres within London, we also collected some imaging and neurocognitive data on the kinds of activations that took place when children were engaged in these different types of problems. So various different strands of data collected there. I'm going to focus particularly on the data that were collected by NFER, really as much as anything for the sake of time, because the rest of it gets into more convoluted detail. But you can check out the publications related to this as the report itself, which is available from the Education Endowment Foundation, shown on the left-hand side there. And there's also a detailed paper on the outcomes, which is published in the Journal of Cognitive Enhancement. And if you're interested in looking further in that, I can send you references, links for those publications. What came out of it? Well, as far as the improvement on the general measures for maths and science progress were concerned, the effects were not large, but remember that these are kind of very much downstream impacts. So, this isn't about, these aren't measures of learning counterintuitive concepts. These are measures of learning that may be affected by a better grasp of counterintuitive context. So we'd expect to see some dilution here. As far as maths was concerned, the data found that there was a relatively small effect size with an estimated additional progress for those in the intervention condition of 1 month. And that wasn't, in fact, in conventional terms, statistically reliable. I think Michael mentioned last week this kind of idea of a ETH security and cost rating. So how much faith can we place in the results, and what's the kind of cost associated with it? So you can see that for that maths result, the ETH rating was a pretty kind of sure outcome with a low cost. For the science measures, there was a better effect size with 2 months estimated progress, additional progress by those in the intervention condition. And that was statistically reliable with the same security and cost rating. Okay, so not huge effects and significant at conventional levels, really only for science rather than for maths. But as I said already, do bear in mind that these are very much outcomes on downstream measures rather than that are on things where we might expect to see change more directly coming out of the intervention. So I think we can also think about this in terms of the nature of the extent of the change and the relative cost of that. So one way to frame this is that children in the intervention group made the equivalent of 1 additional month's progress in maths and 2 months additional progress in science compared to controls. But that was on the basis of 7.5 hours input at a cost of £5.65 or about €7 per pupil. And you might want to think that actually 2 months progress for €7 per additional progress for €7 per pupil is pretty good investment, really. Certainly not something to be sneezed at. So, you know, how we think about the scale of these things is kind of, you know, there are ways in which we can think about it that might make the outcome seem a little bit more positive. The other thing to say is that there were significant improvements to the year 5 as opposed to year 3 sample in both maths and science compared to the active control. And there was also some evidence of a greater effect in year 3 maths for children on free school meals, the children with greater disadvantage, which was also, as I said before, something that we were keen to actually check out. So in general, not strong effects, but positive effects, which certainly suggests there might be something worth thinking about wider deployment of as far as that the kind of stop and think program is concerned. And I think the other things to say is, you know, there's kind of in a way kind of circumstantial evidence in favour of our point about needing to train inhibitory control within the context of the learning itself. But we certainly didn't find any evidence that the Stop and Think program had had any impact on children's general inhibitory control. So that suggests that if there was an improvement and Stop and Think had had some impact on that by promoting greater inhibitory control, it was indeed something within the context of the learning itself that was involved in that. As far as the teachers were concerned, the majority thought that Stop and Think had had a positive impact on maths and science abilities of pupils in their class. And the things that they kind of reported were not just the science and maths performance, but pupils taking time to consider, taking more time to consider their responses before answering questions. So showing that impact of the strategy of stopping and thinking, exercising inhibitory control, and also enhanced confidence and engagement in learning. So of course, this is based on teachers' perceptions rather than direct measures, but certainly it seems to be generally positive in terms of the outcomes. So what do we take away from that? I think what I've tried to do is to illustrate something about the sequence of how we might take a problem, analyze it in terms of the kind of cognitive, neurocognitive processes involved in that, which might point us at strategies for dealing with that problem, identifying strategies on that basis, developing resources to tackle those that can be employed as part of an intervention, and then trialing, evaluating the impact of those. So the project does provide, I think, a more general model of the process from science to intervention trial, though, of course, we've not taken that further as yet in terms of embedding that within actual classroom activities on a kind of national scale, though there is a further trial expected by EIF, which will try to do that. So there is that kind of step of actually embedding in classrooms that needs to be taken as well, and that obviously takes a fair amount of effort. And you know, important things to consider at that point are actually the fidelity of what teachers will actually do when they actually have access to these resources. How far will they deploy them in the way that was initially intended? How far will they use them in different ways which might negate any benefits that of the original intentions? So there's a lot to think of when we think about trying to scale it up to that kind of level. And of course, it's hard to replicate any of this without substantial resources. But I think the kind of key thing to take away from that perhaps is that process that I've described of analysing a problem, developing interventions based on analysis of that problem, and then trialing those. It doesn't have to be on the scale that we use for the Unlock project. This is something that could take place within individual schools if that's what the resourcing will actually allow. So I don't think we need to feel kind of intimidated by the scale of the Unlock project. I think there are plenty of other kinds of approaches, and indeed many within my own research, where we've done things on a much smaller scale, and it can still be very useful for informing subsequent activities, subsequent interventions by schools. Okay, so any further information, contacts you want to gather about that, please do email me if you like at andrew.tolmie@ucl.ac.uk. And you can get more information about the Unlock project from the Unlock website, www.unlock.org. Okay, thank you. Questions? Let me stop sharing the screen.
Many thanks, Andrew. A very, very interesting presentation and very, very insightful. I particularly like the part where you mentioned the Piaget's cognitive conflict approach, which I have introduced in teacher CPD. So basically confronting teachers with contrasting scenarios and then, engaging them in this conflict discussion that would eventually, is intended to help them to change their beliefs, which is something which we know is quite challenging.
Yes.
And I'm really, really interested in obviously seeing more resources, which I think are really beneficial to teachers. My question is, to what extent would teachers then be able to develop their own resources, if that is possible, given the kind of variety that could be provided to them? I'm not sure.
Yeah, I mean, I think it's an extremely good question. I mean, certainly as far as those resources are concerned, our objective always from the outset was that if the Stop and Think program itself worked, that would be made freely available to teachers, and we're still kind of in the processes of trying to set that up. Of course, they then have to actually make use of that, and then that needs to be built into their own classroom routine. There are simpler messages though within this, which I think teachers could actually implement themselves in a relatively kind of strategic fashion without having to rely on building software of this kind into their teaching programs. So there's you may well be familiar with the intervention program called Tools of the Mind, which has also made use of exactly this kind of idea of encouraging pauses for reflection as part of the process of engaging with new material and learning. And I think the kind of key message really from the Unlock project is that actually, if it was productive, it was that encouragement for pausing and reflecting before responding that was the key element of that. And we don't necessarily need software to support that. Maybe it helps in terms of building that pausing and reflecting into the context of the materials that are actually being engaged with. But then, again, teachers, I think, can do that. I think it's about consistency of application really as much as anything else. And if that is understood as the kind of the nature of what needs to be done in a consistent fashion, then I think that's very readily something that teachers can do. That's not, of course, necessarily going to be the case for other types of intervention. Sometimes, there is actually going to be more resource needed for that. But I think, always we should think about first whether it's possible for teachers to simply build things into their own practice based on this kind of evidence. And I think that's absolutely something to be encouraged.
Mm-hmm. Thank you, Andrew. I'm not sure whether there is anyone who would like to answer a question or maybe comment about. I think we've had Ivans who said it was a bit technical at times. Yes, I think it was, but this is just a very short presentation, so you couldn't go into much detail there. But I'm sure there is a lot to read about the area, and specifically maths and science. I think there has been quite some development in the area. Yeah.
Yes, I apologise for the technical detail, but in a way, it's difficult to talk about some of this without without at least touching base with that. I mean, I think the kind of key message really is as we've discussed, a relatively simple one, that one reason that children might struggle with counterintuitive ideas is because they are letting them dominate their thinking, and they need to basically suppress that initial kind of tendency to go with immediate answers and stop that dominance. And at a classroom level, really, that's all that we need to know, promoting that kind of process of reflection. The technicality behind it is obviously part of the evidence base, but it's not something that necessarily has a big impact on the nature of the intervention itself.
We have a question from Klaus Conrad. Klaus, you may want to ask this yourself, but he's asking here, can the stop and go approach be compared to problem-solving strategies, such as, for example, some approaches developed for computational thinking?
Sorry, let me just check that. I'm not quite sure I kind of caught that properly. Okay, so problem-solving strategies. It's well, it's an extremely good question. Let me kind of give you a slightly fuller answer to that, because I think there are some tensions between different approaches. So I've kind of used this talk really to kind of describe very much the kind of idea of embedding particular aspects of cognitive control within the learning processes. So that kind of inhibitory control. And I think there is very clearly a role for that. I think the evidence is, fairly well marshaled to show that that there is some impact on that. I think personally, as somebody who is involved very much in thinking about science learning, especially, but also to some extent maths learning, the problem with focusing solely on inhibitory control is that it doesn't tell us anything about what is actually effective in terms of promoting better understanding of the real content that you want children to engage with. So I think, what I want to say about that really is that inhibitory control is something that you might want to promote, but you also need to think about the processes that you're going to use for actually teaching the substantive content that you want. And problem solving of different types, I think, is integral to that. So I don't think that these things are competing in any way, but I also don't think that they're necessarily particularly closely related. I think it is about trying to marshal these things so that they're occurring in both processes. So in the context of early science learning, for instance, in my own work, what we focused on is, yes, of course, things to do with pausing and reflecting and thinking about things before actually making responses, but also more actively, for instance, in terms of understanding things about forces, why some objects sink very quickly in water and others sink more slowly or float, encouraging children to think about this in an imaginative fashion and to think about what is it that they're not actually directly seeing that might actually lead to these kinds of outcomes. So promoting kind of imaginative engagement with the content, in some sense, as a form of problem solving, thinking about what's actually going on. And I think we have certainly got evidence that kind of approach, even independently of promoting inhibitory control, that kind of approach is an important way of actually producing better understanding of key concepts within the science context. But at present, we're trying to get funding still to extend that work. But I think we need these things as an armory of techniques. And I think this goes back to a point that Michael was making last week, really, that educational neuroscience and the kinds of approaches that we're trying to promote are not about trying to find single magic bullets that are actually going to promote widespread change. It is not like that. It's about trying to identify the key things that might incrementally improve outcomes for children, and then harnessing those collectively so that by bringing these different positive outcomes together, we can start to produce really substantial benefits for learners. But it's bound to be about, I think, trying to promote a variety of things simultaneously. So there's no one answer. It's not just about inhibitory control in learning counterintuitive concepts. It's about what also you do alongside that as well. I think that's really important. So thank you, Klaus, for that question and for facilitating that answer, because I think that's a really important point to take on, I think.
Thank you, Andrew. Not sure whether there is another question from the audience. If not, Erica, if you have a question that maybe Andrew can, you can challenge Andrew a bit. Feel free to do it.
I've got one, I've got three, but I'm going to choose one. You have spoken about the misconceptions in science and maths. In addition to what you have mentioned during your presentation, in what other ways can we ensure that these misconceptions are not presented as strategies within the classroom?
Yes, well, that's if I'm taking the force of that correctly, I mean, the problem is that actually we often, it goes back to a point I made previously about adults passing on misconceptions, because if teachers themselves don't have good understanding of the material that they're actually dealing with, then of course there is always a kind of potential problem with that. I like to refer to a story that was told to me by my colleague Denis Marichal, who I mentioned earlier, and an experience that he had once. He takes a regular slot half day a week, helping out in his local primary school with science teaching, as a kind of teaching assistant, not a direct instructor. And there was one particular lesson he talked about where they were dealing with insulators, and the teacher said, and metal is a good insulator, which is, of course, exactly the opposite of what is true. And he was moved to intervene at that point and saying, I think you'll find that's not right. It's difficult. I mean, I think we need, obviously, as far as possible, for teachers to have a better conceptions of the things that they're actually dealing with. And I suppose, you know, there is a certain amount of activity through CPD that can be used to promote that better understanding. I think a kind of less obvious answer to that question, though, is that in some senses, it doesn't necessarily, if we're approaching this in the right fashion, certainly not at primary school level, it doesn't necessarily require the teachers to have really very much greater understanding than the children, if you approach it in the right kind of way. So if you present children with the kinds of scenarios that I was talking about for objects floating and sinking, and let them explore that themselves and try to explain that for themselves, then in fact, even if the teachers don't necessarily have a good grasp of what's going on, it will still produce progress on the part of the kids, because they engage with this in an imaginative fashion, start to think about what's actually involved there. And so just to kind of go perhaps into a little bit more detail about the work that we've done on that, as I've indicated, that was focused on objects sinking or floating in a tank of water. And what we did for this was a simple kind of classroom exercise. Myself and my PhD student at the time, Selma Dunderkerke, led this ourselves rather than asking teachers to do it. But I think, you know, this is obviously a task that could be easily done by teachers themselves. Basically, what we did was just have a large tank of water at the front of the classroom, and we had a big stone and a large tomato, and we put them into the water. And we asked the children, first of all, before putting them into the water, what they thought was going to happen. So that kind of prediction element that I was talking about before. And then we showed them what actually happened. We asked them to closely observe what had happened and to provide descriptions of that afterwards. Now, with stone, the big stone, it just sinks straight down, you know, with a clatter, as you may imagine. If you get the right tomato, and it doesn't necessarily require a great deal of exploration to do this, you get a big, what we call in the UK, beef tomato, then what happens is a very interesting thing where it sinks to start off with, and then actually it kind of rises back up again and floats, because it's just very, very, very slightly less dense than the water itself. And so you get that kind of nice outcome of the tomatoes apparently starting to sink and then going back up again, which provides a nice kind of illustration of something of the forces that are actually working. There is a kind of resistance from the water that's pushing the thing up. So we got children to describe what they saw. And rather than immediately leaping to get them to explain what had gone on, what we did was we asked them in groups of 3 to play a little game where one of them would be the water, one would be the stone, and one would be the tomato. And what they had to do was just simply talk to each other about what had been going on between them to lead to these outcomes. And it was only once they'd engaged with that we asked them to actually explain what was going on. And immediately what we saw was a dramatically greater incidence of what we call mechanistic responses, where they're talking about the actual process involved, the forces involved. They started to talk about the water pushing back up, because now they'd actually had some means of imagining what was going on and engaging with that. we kind of followed that through with kind of further objects for them to make predictions about and explanations about, and started to introduce in a later stage some kind of more technical vocabulary around up thrust and down thrust, etc. By the time we got through to the end of that session, about 40 minutes in total, we had a very substantial incidence of very high level accounts of what was going on the part of the children. Now, the other further thing to add to this was that this was a session that was run in with year 1 to year 3 classes in a school in one of the most deprived regions of England, where we have, it's phenomenally high percentage of children with free school meals, very disadvantaged backgrounds, producing these high level responses even at 5 to 6 years of age after engaging with the content in the right kind of fashion. And the teachers, who possibly didn't have very good explanations as to why the tomato floated and the stone sank themselves, were really engaged by that. And several of them said to us afterwards that they'd never heard their children produce this kind of explanation before. They didn't think that they were capable of it. So the point is that if you think carefully about the nature of the engagement and the kind of problems you're asking children to solve, then you can go a long way with actually promoting the kind of greater development without the teachers necessarily having to do much more than simply kind of manage the process of engagement on the part of the students themselves. So there's very productive ways, I think, of doing this, which don't require substantial upskilling by teachers. Yes, more time. That's the saying.
Okay. Any other questions that you might wish to ask?
Marie-Therese has her hand up.
Yes.
First of all, I apologize because my internet is a bit intermittent this afternoon. Just when you were talking about the study that you did with the students, I mean, those slides that you shared, it seemed like sort of just, I mean, I would call it good pedagogy, a good way of tackling mathematics, thinking, reflecting, giving various options. Can you sort of go into a bit more detail about your interpretation from a neuroscience point of view, sort of as a lay person, so to speak, somebody outside neuroscience? I would say that's good teaching. The teacher made some good connections between different representations. Sort of that is how I would, interpret it, having no background in neuroscience. So if you can sort of talk us through it, in more detail from your perspective.
Yes, I mean, I think it goes back to something that Michael was saying last week, which I think is important to I suppose see about what it is that we're trying to do here. So as he said, it is unlikely at this point in time that what educational neuroscience, that whole kind of package of approaches that we're talking about here, which obviously go a bit wider than neuroscience itself, it's unlikely that that is going to produce stunning new strategies which are going to make a big difference to learners' outcomes. Indeed, as I'm sure he said, and he didn't say it last week, he usually says it, so excuse me if I'm kind of misremembering that. Mostly what we're doing at the moment is trying to find ways of producing evidence to help us understand why some of what teachers do is effective and why some of the things that teachers do is not effective. And so actually the idea that this is good pedagogy, I think is absolutely fundamental. I think, we would hope that good teachers would be using these strategies already. But what this does is to explain why it is that is actually important. And therefore what the evidence does is to enable us to say to teachers, okay, there is this thing that some teachers do, and we know that it's really productive, and this is the reason why. Therefore, it is something that would be a good idea if people were adopting more consistently and more uniformly. And I think that's really very much the kind of nature of the exercise that we're engaged in at the moment. It's about that process of really trying to marshal evidence that helps us refine the kinds of things that probably are in most instances going on in well-run classrooms already. But we need to kind of sift out what's good and why it's good from what's less productive, and think about why that's less productive. Does that help? I think it's not about appeal to the evidence. It's really just about providing an evidence base that actually kind of makes it plain why teachers should be doing some things rather than others.
Thank you. Yes.
Maybe we can take one final question. Erika, what do you think?
Mine are very, very general, not particularly specific. I'll choose another one. In the past decade, there has been tremendous increase in neuroscience research on mathematics and science learning, while the field of mathematics and science learning has been proposed as an ideal workspace for making applications of neuroscience to education. What are your thoughts on this?
Well, you're right about the maths and you're not right about the science, unfortunately. Yeah, there's been a huge amount of work in the context of number development and maths, which I think really is starting to kind of begin to inform educational practice. I wouldn't say it's quite there in the way that it is within the context of literacy and teaching reading and writing, where I think the understanding is perhaps in many senses more deeply embedded in classroom practices. And supported indeed, well, certainly in the UK by government policies that are promoting those kinds of things. The maths research has been very extensive, and it's thrown up a lot of debates. What I think comes out of that is that people have had previously made big appeals to the idea of initial kind of sensitivity to number being an important part of children's learning of number and mathematics, and that after a lot of studies have looked at this, that really doesn't seem to be particularly the case. It's actually number specific things which really are the kind of big driver of learning, and in particular things to do with number knowledge, understanding numbers, understanding symbolic representations of numbers. These are really the key things. And I think anyone who's a maths teacher would say, well, that's a surprise then, because but that kind of goes back to what I was saying before. What it does also, I think, show us is the particular kinds of usages of working memory in particular. So the capacity to kind of retain, process information mentally is also a key aspect of developing more proficient arithmetical skills, mathematical skills. That perhaps is a little bit more kind of novel. It kind of goes back to some of the things we were talking about in the Unlock project, that actually management of information, strategies for managing information when solving problems is likely to be important. It points at a very kind of particular role for mental arithmetic, I think, which is likely to be important because it's about learning to actually have strategies for actually managing numbers mentally without having to write things down. So those things, I think, are starting to feed through into classroom processes, particularly perhaps in terms of the way that the problem-solving sessions are actually structured, and also, kind of interest in memory systems more generally, how those actually play into that. The Department for Education in England, as I think many of you will understand, education is a bit weird in some senses in the UK because it's a devolved responsibility. So it's managed separately by England, Scotland, Wales, and Northern Ireland. The Department for Education for England is certainly, as part of its teacher training programme now, insisting on good engagement with the understanding of the cognitive processes involved in memory and understanding the implications of that for consolidation and practice within classrooms. So a lot of that is actually happening. The position in science is unfortunately very much less well developed. There is not very much research, and what we've been struggling with for some time really is getting the research on the kind of neurocognitive processes that might be involved in that scaled up to the point where we can start thinking about interventions in more productive fashion, and we're well behind maths and literacy as far as that's concerned at the moment. But I think we are generating new ideas. I think the problem, as ever, is in many senses a political one, that reading, writing, and arithmetic are seen by governments as key skills that children need to engage with and to be proficient at by the time they leave primary school. Even though science within England is an official part of the national curriculum, there is no particular political expectation that children should engage with science or have a good understanding of science by the time they leave primary school. I think that's fundamentally mistaken given the context of my soapbox for a moment, but given the need for better understanding globally of scientific concepts. And the pandemic revealed that, and issues around, questioning of vaccine programs and things like that, but also, of course, in context of climate change. These are areas in which we need people, citizens generally, to have a good understanding of the science involved. And so, promoting science, early science learning, I think is fundamentally important, but it's lagging behind considerably at the moment. Well, I'm not quite sure, except continually kind of making the point what we do about that, but we do get better. I think I draw out one other point, Erica, from that, which is that, which kind of goes back to some of the things that Michael was saying last week, and some points that I kind of was echoing in the talk before. That I think the other thing that we've learned, I think, from this kind of research is that it's very unlikely there is any general pedagogical approach which is going to be effective. There may be some strategies that are helpful. I certainly have a strong belief in Vygotskian notions of scaffolding and the use of that, but also, peer dialogue, I think, is important. But the way in which learning happens in learning to read, learning to write, learning how to do arithmetic, learning science, the processes, the neurocognitive processes involved are completely different. And there's no one strategy that is going to work for all of those. We need different strategies for different areas of the curriculum, and that's, I think, absolutely, totally evident from the work we've done so far. The only common ground that I can detect is that there is something similar between all those areas in terms of being able to understand and process symbolic manipulation. That seems to be core to everything. And that's maybe something to do with the nature of the kind of way in which manipulation of symbols plays into use of language and the cognitive organization that results from that. But that's a speculation really at this stage. But generally, the pedagogies, we need to think about strategies for teaching each of the different areas of the curriculum, because it's not, won't be any generality. I'm fairly confident of that.
Thank you, Andrew.
Thank you.
I think it was another very insightful presentation from your end. And I think these two webinars have really opened up a lot of discussion about education neuroscience in the local context. I thank Erica for coordinating all this, and for Michelle for her support. We will be uploading the recording of this webinar later on the faculty page, but we will also be sending emails to inform others who were not able to attend during this time. We promise that we'll be back. We'll be back in October with a new series, the Connect to Learning series that myself and Michelle coordinate. But this time we'll do it together with Erica, and we plan to have around 8 webinars, weekly webinars, over a 2 or 3 month period. So hopefully we'll engage practitioners and other people who would be interested in this area. Thanks again, Andrew, and thank you all for being part of this here today. Have a nice afternoon.
Thank you. Thank you.
Cheers. Bye-bye.